We have okay, so good afternoon, ladies and gentlemen, and welcome to the session number 10, which is called Potential of New Solutions, some evidences. We will have 3 very interesting presentations that touch highly important technologies for energy security, energy resilience, and also solving the energy crisis in Europe. Namely, we will hear a presentation by Dr. Giuseppe Dell'Olio, first on the sustainability on cogeneration. Cogeneration has a major potential indeed in Europe and worldwide. Then we will move to Janez Dolšak, who will talk about energy efficiency in the residential sector, energy efficiency being identified as one of the most important measures that we have for energy security presently. And the final presentation is then on hybrid heat pumps and their impact on electricity supply. Again, heat pumps being a very strategic means now in the European energy crisis. So 3 highly relevant presentations, which we will hear in a while. I would suggest, because of the time limitations that we always have in our sessions, that the presentations would be about 15 to 20 minutes. Then we have some time, maybe up to 10-minute time for discussion and questions. And then at the end, we could then have a wrap up indeed on the themes. So the first presentation will be by Dr. Dell'Olio from GSA in Italy. Has a long experience in energy with different agencies, with Enel, etc. Now he is with GSA in Italy, and he will talk about how sustainable is cogeneration, and he presents a long-term, real-life evaluation, and we look very much forward to his presentation. And now I hand the floor to Dr. Dell'Olio to give his presentation. So the floor is yours, Giuseppe.
Thank you very much, Mr. Lund. I'll now share my screen, which I did before, so I have to be able to do it now. I assume you can see my screen in this moment. Can you?
Yes, indeed, it's fine. And if you just push the presentation mode now, then I think we have your full presentation on screen. Now it looks great. Thank you.
Okay. Thank you very much. So good afternoon. My name is Giuseppe Dell'Olio. I'm with GSE, and we are basically a public authority that incentivizes renewables and energy efficiency. And that's why we have a long experience, not only in cogeneration, but of course, cogeneration is one of our main topics. Due to our job, we collect numerous operation data, and have been doing so for many years now. So this enables us to draw a few conclusions on the best way to perform cogeneration, and especially on which technology is the most suitable for cogeneration. We analyzed more than 600 generating units, many technologies. We will focus only on the three main ones: gas turbines, internal combustion engines, and steam turbines. Once again, I'd like to highlight that our data are not laboratory or simulation data. There are real-life operation data collected between 2011 and 2019, with something close to 12 million equivalent operating hours. So the conclusions we will see are based on reality. What's the way we used to draw some conclusions? We calculated a few efficiency indicators, which You see listed on the screen: electric efficiency, thermal efficiency, overall efficiency, the sum of electric plus thermal efficiency. Then we have power to heat ratio. I will elaborate on each of these, of course. Equivalent operation hours and load factor. Not only did we calculate these indicators as weighted averages, but we also performed some statistical correlation among couples of them, between couples of them. So, namely, we correlated or looked for correlation between operating hours and electric efficiency, operating hours and load factor, electric efficiency and thermal efficiency, and electric efficiency to commissioning year. Let's give just a few explanatory words about each indicator. The electric efficiency is, of course, the ratio of electricity produced by the cogeneration unit in a given year, ratio to the energy consumed to do so, to produce that electricity. And that energy is, of course, contained in the fuel used. Thermal efficiency, conversely, is the ratio of heat produced in a given year to the energy, fuel, consumed to do so. The overall efficiency is just the sum of the above. Maybe less known is the power to heat ratio, PTOH. That's the ratio of electricity to useful heat produced by a cogeneration unit in a given year. So far, we have seen ratios of output to input. Those are the efficiencies, electric and thermal. Now we see a ratio of one output to another output, electricity to heat. What's the meaning of this ratio? Well, a unit that produces with a high power to heat ratio produces a large amount of valuable energy, and that is electricity, as compared to heat. So between the two outputs of a cogeneration plant, electricity is considered more valuable. So a high power to heat ratio means a comparatively high amount of valuable energy produced. Again, a high power to heat ratio indicates that the heat carrier, for example, steam in the case of a steam turbine, but it can be just the exhausts in the case of an engine or a turbine or a gas turbine. A high PTOH indicates that the heat carrier was exploited efficiently. So the heat carrier produced a significant amount of electricity before being sent to the atmosphere, before being dispersed to the atmosphere, or, sorry, not dispersed, used for thermal purposes. No, the heat that is dispersed is not useful at all. I was saying something wrong. Another indicator is the equivalent operating hours, H. That's the number of hours during which the generating unit would have been in operation. That's why these are equivalent hours, not actual hours. Would have been in operation if it had constantly been kept at maximum load. What's the meaning of this indicator? When it is close to 1, this means or suggests that there were few starts and stops for the unit, which is a very, very favorable operating mode. And in this favorable mode, the performance of the unit is expected to be high. It is easy for the unit to be performant. Conversely, a low number of equivalent operating hours indicates that starts and stops have been numerous. Of course, we might theoretically think that a unit has only had one start and one stop in 1 year, and then nothing else has been kept out of operation for the whole rest of the year. But that's unlikely. When we see a low number of equivalent operating hours, the first thing we must think is that there were many starts and stops. that's a more realistic scenario. Now, the equivalent operating hours is a good indicator, but does not provide all the information we need. So when it is high, okay, we know that the unit has been operated for a long time during that year. So of course, starts and stops have been few, because otherwise we couldn't have reached that high number of equivalent hours. On the contrary, on the other hand, when the number of equivalent hours is low, we have no specific indication. In this case, two things are possible. There were few hours at full load or many hours at partial load. Why partial load, for example? Because the starting time is very long for that unit, and there were several starts. So we don't know which of these occurrences is the true one. We need more information. That's why we also divided the equivalent operating hours number by the actual yearly operating hours. By the way, everything I say is referred to 1 year, from the 1st of January to the 31st of December. So we divided the actual, the equivalent hours by the actual operating hours. And this ratio we called the load factor, FC, fattore di carico in Italian. Of course, a load factor is always less than 1. If it is close to 1, then the generating unit was kept close to full load. How was it possible? Of course, because starts and stops were quick, took place rapidly, and as a result, heat dissipation was limited, because heat is typically dissipated during starts and stops. If we have rapid starts and stops, heat dissipation is low. So these are the results. Just a few explanations. The wording small scale indicates a unit between 60 kilowatts to 1 megawatt, whereas whilst micro means something between 5 and 45 kilowatts. When there are both wording, of course, micro prevails. I will not talk about minor technologies, or minor in this study, of course, like ORC. Let us focus on microturbines, turbines, internal combustion engines, and steam turbines. Green means excellent performance, yellow means average, and red means poor. Now it's easy to see that the most green are for internal combustion engines in the different sizes. We have a very high electric efficiency, quite good overall efficiency, a very high load factor, and a very high power to heat ratio. These excellent performances decrease somehow as the size of the engine decreases. So we see some red appearing in the micro below 45 kilowatt area. But altogether, performance is very good. As to gas turbines, well, there is some good or some average, but there is also very much red when it comes to load factor, for example, or even to electric efficiency for small-scale turbines. Even worse when we talk about steam turbines. Here we see a lot of red, low efficiencies, at least the electric efficiency. The only very good performance is overall efficiency for above 1 megawatt. But apart from that, everything is red or yellow. I like to draw your attention on the fact that, for example, a load factor of 89 was deemed very good in the case of engines, but became red in the case of gas turbines. Why? Because in the first case, it is associated to a relatively low number of equivalent hours, and this is a percentage. whilst in the case of gas turbines, the load factor is associated to a much higher number of equivalent hours. So life has been much easier for gas turbines, and in spite of this, the load factor is low. Engines, even if used for fewer hours, lower number of hours, so with more starts and stops, in spite of this, they had a very high load factor. So load factor always has to be assessed together with equivalent hours. Some statistics and just a few words to remember what we're talking about. We will mention coefficient of correlation, which if equal to +1 means direct proportionality between the two quantities being studied. If it's -1, it indicates inverse proportionality, and if it's 0, means no relation at all. And the coefficient of correlation can be anything between -1 and +1. We will also mention a beta-1 coefficient, and that's the use of it is shown in this formula. It's the angular coefficient of the straight line describing the relation between y and x, the ideal relation, of course. First of all, we will see the correlation between electric efficiency and thermal efficiency. I highlighted the lines I'd like to draw your attention on, and probably the most important here is the very last one. Everything is ordered here in the following slides, with beta decreasing from top to bottom. So when beta is very small, -2, the correlation is very high. It's an inverse correlation, of course, because the correlation is negative. So it's a strong inverse relationship. This means that the amount of heat wasted is low, because if when electric efficiency decreases, thermal efficiency increases. So there is very little waste of heat. If we lose some energy produced because the electric efficiency reduces, we gain something on the thermal side. This is possibly influenced by the method of assessment, because for very small micro engines, but also turbines, a special regime is in place. But this proves that the method we're using is fruitful, is correct. Let us now see correlation between electric efficiency and the commissioning year. You see here in the middle what I would like you to notice, and the conclusion is that both for internal combustion engines and for gas turbines, the electric efficiency is basically independent of the year of commissioning. This means that these two technologies have reached their maturity. No improvement in electric efficiency has been reached during those years. This may sound as bad news, but it's actually good news, because we have something to rely on. Technology is mature. Again, correlation between equivalent operating hours and electric efficiency. You see in the two highlighted lines that for small-scale steam turbines and for small-scale gas turbines, the correlation is quite strong. High correlation, high coefficient of correlation, and high beta-1. This means that these two technologies work well when they're used for a long time, and this means continuous operation. They are best suited for continuous operation. When we only operate them for a limited number of hours, which reasonably implies frequent starts and stops, then the electric efficiency drops. Again, equivalent operating hours versus load factor. In this case, I'd like you to notice the behavior of back pressure steam turbines. The correlation is strong, very strong, 0.9, and also the beta is quite high. This means that the starting times are long. These technologies are not suited for intermittent operation. So, a few conclusions. As you can imagine, the best technology, in my view, is internal combustion engines, which have the following features: about 1 megawatt. They have a very high power-to-heat ratio. We saw it in the table, in the colored table, and very high electric efficiency. Both these indicators decrease with the engine power, but do not decrease very much, actually. The overall efficiency even increases as capacity decreases. So, in spite of all in all, a very good behavior. The load factor is always high, irrespective of the power we're talking about. And it is high even if the equivalent operating hours are few. This means that these engines can be started and stopped rapidly. So they're very flexible, they're very good when where a high number of starts and stops is needed. They are suitable for this. Finally, they have reached their technical maturity because there was no increase in electric efficiency no significant increase from 2011 to 2019. Second best are gas turbines. They have a good or even excellent overall efficiency. Unfortunately, the electric one is quite low. Again, at least for the bigger turbines, electric efficiency does not depend significantly on the equivalent operating hours. So these turbines can be used for intermittent operation if needed, up to a point probably. This is not the case below 1 megawatt, because below 1 megawatt we have a positive correlation between electric efficiency and equivalent operating hours. So these turbines, the smaller ones, well, not that small, but small all the same, below 1 megawatt, are best suited for continuous operation. You should not use them for intermittent operation. The power-to-heat ratio is generally lower than for motors. There is an exception. Also, gas turbines seem to have reached their technological maturity because the electric efficiency does not depend significantly on the commissioning year. So, second best technology. The third and worst, I'm sorry to say, is steam turbines. They have low efficiency, low power-to-heat ratio, and low load factor. The only good thing is the overall efficiency. They suffer from load variations. This is at least the case for the small-scale ones below 1 megawatt. How can we see this? Because there is a strong direct correlation between equivalent operating hours and electric efficiency. We saw this in one of the tables, one of the previous slides. There's also a strong direct correlation. This is independent of the power between load factor and equivalent operating hours. This also means that they have long times. They need long times to reach full regime. They have long starting times. So they are not very apt to variable load. They're not suitable for that. They're not suited for intermittent operation. Thank you very much for your attention. And of course, I'll be happy to answer your questions, if any. Thank you very much.
Thank you very much for a very interesting presentation on the comparison of major CHP cogeneration plants in real, and this was important, in very real environments. So, would we have any questions? I think we have time for one or two questions from the audience here. If I may start by the question now, thinking about the fuel of these cogeneration plants. So, if you think about internal combustion engines versus gas turbines, or the traditional steam turbines with back pressure. So, how flexible would the ICE be in terms of the fuel choice? And in particular, we think about sustainable fuels in the future.
In this analysis, we only chose units that were fueled, that was gas fueled. This
Right.
to avoid any disturbance in the comparisons. That was a deliberate choice. Of course, basically all of these units can be fueled by renewable fuels. That's a good idea for a future study. We can compare a single technology and the performance of that technology with different fuels. We have numerous examples of, for example, gas turbines fed with biofuels, or, for example, steam turbines fed with solid biomasses, which of course have to be milled before being burnt. There are technologies for that. I hope we'll have a similar presentation next year, comparing fuels rather than technologies.
Yes, and indeed, the presentation comparison now was very useful in a way. It gives now guidelines also on the use of CHP, and we know that CHP will be important for the energy transition. We need flexible power, and indeed, you show that, for instance, ICE engine CHP cogeneration could be a very viable option to complement then as a variable renewable energy because of its very high flexibility.
Yeah, that's what we think.
Yeah. So, any other questions to Dr. Dell'Olio? If not, then we thank you once again for a very interesting presentation.
Thank you for managing.
And thank you. And then we will move forward to Janez Dolšak, who is an economist from the University of Ljubljana, and he has been working on energy, many aspects of energy efficiency for a longer time, and now today he will present in our conference a presentation paper called "The Historical Evolution of Determinants of Energy Efficient Retrofits in Residential Sector." So we're going into buildings, into households, a very important sector indeed for the present energy crisis as well, as we try to combat energy poverty or energy scarcity this winter. So what I do now is I hand over to Janez, and he will give his presentation. Let's try to keep it around 20 minutes again, as the previous presentation, and then we have some time for a few questions. So the floor is yours, Janez, please.
Okay, so hi also from my side. I will now start sharing screen. Okay. So can you see it?
Yes, we can see it well, and just put in the presentation mode, then we are ready. So go up and then just choose the presentation mode, then
So
normally it's down in the right corner. Down right corner, there is the down right corner. You see the presentation mode. Yeah.
Okay, I will try a little. Sorry, I just checked. No, it's not sure.
Typically have down in the right corner. There is a screen, kind of a symbol. Just push that.
Okay, I think is the right one now. Can you see it?
Now we can see. Now it's excellent. Everything is okay.
Okay, sorry.
No problem.
I
no
changed
problem.
something probably. So thank you, Mr. Lund, for the excellent introduction into also residential energy efficiency. I think that now, if I may say something about it, so we are seeking new ways how to solve energy crisis current, and we somehow neglected the energy efficiency. So I will put some words about the energy efficiency now, what we have done. So as a part of the recent research on the residential energy efficiency, we were seeking for determinants that impact the consumers to invest in energy efficiency. So this part, what I'm presenting today, it's let's say the last part in the series of research. Now, what I wanted to do now is to make a comprehensive overview over the determinants that we have already found and also that the literature have found. And I think about using, I thought about using data science in order to gather all this information to build some map of knowledge in order to see from, let's say, from the sky from the deduction to imply some, let's say, policy implications. So let's start with the motivation. We all know that energy sector, so the residential sector, is responsible for almost 1/4 of final energy consumption. And also the European building stock is very old. And the progress of energy efficiency is very slow. That's why European Union and European Commission already enacted some directives and laws according to increase the retrofits rates. Among this is Fit for 55, which aims to achieve climate neutrality till 2050 by reducing energy emissions and also to increase energy efficiency. Also, what they have done, they revised the energy efficiency directive, which states that there should be increase 1.5% each year in the energy efficiency. And the other directive is energy performance building directive, which also says, and the recent revision, which was accepted this year in the autumn, is setting some regulatory framework to build new scheme of supporting retrofits. So we all probably agree that there are huge energy saving opportunities in residential sector that we have to somehow use it. We can insulate walls, we can change windows, roofs, etc., many other. Despite the availability and economic viability of energy efficiency measures, their realization is very low. And we label this gap as energy efficiency gap. So we know that at one side, there are some opportunities of investments which are also economically viable, but people, residents, just don't decide for it. And beside that, there are a wide range of potential benefits of energy savings that increases your disposable income, that reduces so aggregate unemployment rate, and also to increase the asset value. And what is the reason behind why people just do not decide for the investments? There are several barriers that hinder investments, but there are also some drivers that foster the investments. And several energy instruments have been introduced, like I said, from the European Commission to tackle these issues, such as subsidies and also informational measures and many others. So in order to design the effective policy measures to enhance future energy saving measures, policymakers must be informed about the condition of buildings, about the behavior of consumers, about also the heating system that they have in their buildings. And in this research, I tried to identify which determinants have the most important influence in decisions for energy retrofits, and also to find some connections between these studies. And that's why, first of all, I need to use appropriate taxonomy to make a comprehensive literature review. So just to find all possible, maybe not the all, but as much as I can, determinants, all barriers and drivers that can somehow increase or decrease the probability of investment. So I take a look at different taxonomies, and I use at the end the taxonomy, the last one from Hrovatin and Zoric, which is extension version of previous categorization, and uses information and policy measures as a first group. The second is economic factors. The third is household socioeconomic characteristics. The fourth is technical factors, building characteristics. And the fifth group is behavioral factors. So all these groups consist of barriers and drivers that can somehow impact on the decision to make energy efficient investment. So just for the start, I will only go briefly through the main categories, because this is not the point. I just wanted to emphasize what kind of literature review I made in order to be able to use bibliometric tool, data science tools, because somehow you have to know what you are searching for. So first group is information and policy measures, which consist of regulation, fiscal support, energy audits, information, social network, and informing homeowners. The bold numbers here are the number of studies that I have found which stated there is a positive effect, neutral or negative effect. But as I said, I won't go through in detail, but if you're interested in, I can show you. The next group is economic factors, which consist of retrofit costs, savings in energy expenses, economic viability, energy prices, time horizon, and other economic factors. The third group, socioeconomic characteristics, consist of income, age of homeowners, education, and other socioeconomic factors. The technical building characteristics consists of age of the building, location of the building, its technical parameters, and then also better expected living condition and better expected comfort, thermal comfort. And the last is the behavioral factors, which consist of awareness, lifestyle, and other behavioral factors. Using all these identified determinants, I go to bibliometrics. We know, you probably heard of bibliometrics. It's a data science method. There consists of different methods, and now having a lot of available data, it offers us to resort us to deductive reasoning. So looking from the sky, thinking a bunch of different documents that have been published, thousands of them, and trying to deduct something. Okay, but despite the large volume of work describing, I didn't found in this area, I didn't found a comprehensive quantitative analysis, as I said, in this part of research. Therefore, in addition to the literature review that I made, I also apply some data science method to somehow not only to see these barriers that I already identified, but to see the connections between them. which are, let's say, studied together and which are cited by the common authors, etc. But how I did it? Maybe just a few words about the bibliometrics. It consists of 4 main bibliometric methods: citation analysis, co-citation analysis, co-authorship analysis, and the co-word analysis. Typically, researchers use the first 3, but I use the 4th one. But I didn't limit it myself to the words that are described as a keywords, but I take a look at the abstracts. So like a data science, I take a look all abstracts of all files that I found that are somehow selected. I will show it afterwards. And I take a look all words that are mentioned in the abstract, because I believe you usually put the key results, the key determinants in the abstract. So I did somehow assume that the abstract words are let's say the set of identify factors, not only the identify factors, but also research factors. So what I did, using somehow very refined selection, but also very broad, I allow myself not to lose anything out. But also, on the other hand, I also refine search using some, which is not presented here. After I run this selection, there I get around 1,200 different documents, which was published, but not only papers, but also conference proceedings, books, book chapters, and some similar. So what is written here? And then what I did, after I first ran the analysis, of course, I get many different words that are not even useful, which are not determinants. And then I go through all these words and I search for determinants that are somehow related to this area. So that could somehow affect the investments in energy efficiency or not. So the main statistics of it, I found, as I said, more than 1,000 documents from 322 sources between 1903 to 2022. The annual growth, as you saw, somewhere from, so the average annual growth is 17 documents per year, but as you saw, after 2010, there is a large increase in the research in this area. On average, 33 references and 21 citations. On average, also almost 3 authors for each document. Only briefly through the most sources. So the most sourcing paper or journal is Energy and Buildings, Energy Policy, Building and Environment, Applied Energy. Okay, as expected, according to the area of research. The subject areas also as expected: energy and fuels, engineering, construction and building technology, etc. Okay, so what I found? Identified 85 determinants that can be clustered, as you will see in the graphical presentation afterwards, can be clustered into 4 clusters. One cluster can be named as thermal comfort. The other is energy cost. The energy cost, and also it consists also of economic factors. The third is environmental impact, sustainable retrofit. Also, we will see so different determinants, but when you try to build a story of it, you can, let's say, see some results. And the last one is environmental awareness, related also to behavioral change. Okay, so this was the results. Here we see 3 clusters. Okay, because of these controls, I cannot see the last one, the violet one. So the red one is a thermal comfort. You can see here people, not people, but researcher identified, let's say thermal comfort, indoor air also, and other thermal characteristics, also energy saving, energy security. So that's why I name it thermal comfort as a main driver here, but it's related to thermal characteristics and also to energy saving. The other is cost saving, the blue one. It's about more about energy cost, also household income, financial benefits, total costs, and as I said, many others that are also included here, but also energy price, etc. The third one, it's climate condition, also related to environmental impact and other environmental aspects. So you can see from it that there is some story that similar things are researched together or maybe identified together. And the last one is a social practice, social network, also environmental awareness. So the behavior change using daily routine, social practice, social network. Okay, and the next analysis, sub-analysis that I made it here is the historical. Okay, wrong button. So the historical evolution of it. Here I, let's say, select 3 or 4 periods of time according to the available number of documents. And I try to find which determinants were identified in each period. And then these documents that have identified these barriers or drivers, they were citing some literature, previous literature. Okay, so let's say if we take a look at the second period, we see here the thermal characteristics were identified, environmental impact, consumption behavior, etc. But taking a look at the, for example, thermal characteristics, we see that these authors that identified this factor were also trying, so citing some authors that identified indoor air as important. So now we can see some relations between. They probably studied also the factors that were identified in the previous period. For example, if the location rural is more important, but they found that probably they found that the thermal characteristics are more important. They just included location, for example, a rural location or indoor air quality. The second also, and the story goes along, environmental impact is somehow consists of several factors, environmental impact from the previous, which is as expected, and also energy cost, which was, let's say, in this period, getting more importance, also environmental impact, and etc. If we take a look at the third area, also thermal characteristics are very important, and the studies that identified these characteristics they were citing many other aspects of here. Also policy measures. If we can see below, there are Energy Star, energy efficiency policy. Sorry, there is a mistake. I mean, I made a mistake now. Energy Star is related to the emission reduction, not to thermal characteristics. What I want to say is efficiency policy in EPC certificates, so energy performance certificates. The interesting thing is that emission reduction that was identified was cited in previous period from environmental impact, but also from Energy Star. I found it very interesting because the results of Energy Start program said that they increased decreased emission for around 5% on aggregate. So that's why probably studies cited Energy Start as being a source of emission reduction. And also in the last period, the household income, low income comes so it emerged, getting more importance, also cost saving, maintenance cost, etc. So this is the evolution, only briefly. So to conclude, according to these streams that I presented, I'm able to identify the whole historical development, what was identified in each period, and what are the relations between them. I did it in more detail in the paper. So the analysis of contents of abstracts allows me to visualize the current state of the knowledge. And lastly, the type of analysis is usually equipped with a large collection of data and analytical approaches. It can support some policy measures, which I believe that should not be neglected. Okay, thank you for your time, and I'll be happy to answer your question.
So thank you very much for interesting presentation as well, and for very sophisticated analysis, I would say, on a very important topic. And I'm sure there's interest from our audience also to make maybe a few questions. I open the floor to any questions. It's always difficult when we work virtually online with a question. So let me maybe make a question here. Just a few questions. First one is on the number of determinants. You had 85 determinants. So when you go analyze the papers, I guess a single paper may actually address a few determinants, not just one single. So it may be that one paper would that, in a way, on average, if you think there's several factors that one paper would actually address, or would it be just one that you picked, the most important determinant, or did you take this multi-determinant then into account?
Okay, if I understood correctly, thank you for your question. You're asking if these papers that I have included in the analysis were identifying more than one determinant.
Right.
Yeah, the funny thing is here that after I made a literature review, after I identified this, these papers were definitely identifying more than one. But after I conducted the bibliometric analysis, honestly, I do not know what these papers are saying. So I assume that my way is okay, as I say, my way of, so I really refined research, the search of these documents, and I believe this is the accurate, but I'm sure that not all documents are included, and I'm sure that not all documents are not mentioning, not saying, or maybe not talking about the same thing that I'm researching. But definitely they are identifying more than one barrier or driver.
Right. I could imagine that energy and environment goes very often hand in hand. So the environmental consequences and the energy, they would be quite often a pair of determinants that comes along in the papers. Maybe another question is there's the final slide where you showed this flow chart in a way to 3 periods of time. And I wondered the 2 last periods where we will look from 2017 to 2019, and then from 20 to 22. There's a major change in one of the factors we call thermal characteristics. And 2017, 2019, the thermal characteristics was very large actually.
Yeah.
And then when you go 5 years later, it's in a way disappeared. Or let's say it was broken up to other factors like thermal comfort, etc. And why would that be? So would there be some kind of change in European policies or something which, yes,
Okay.
here I think it's very, so the red bar is changing pretty much. So
Yeah,
and
it's really funny, but probably these papers that identify thermal characteristic in the previous period, they did not identify or did not even research this as a key factor.
right.
But I see that those that have identified some other factors somehow cited these factors. Some of them are similar. For example, thermal comfort. You see them, thermal
Yeah,
comfort,
that's right. That's right.
but
Yeah,
not many others. You
right.
identified correctly that there is some dispersion of the thermal characteristics,
Yeah,
of its importance.
and there may be the kind of big framework for energy efficiency changing, or some emphasis in directives, etc. Maybe there's some factors that change the in a way the factors, or let's say transform the factors in some way. Yeah. And anyway, very interesting. So
Okay.
any other questions to Janez? If not, so thank you once again for a very relevant, interesting presentation, and good luck with your further analysis too.
Thank
And
you.
so then we're moving to our final presentation this afternoon. We have Dr. Wang from ParisTech from France, and the presentation is now on heat pumps, and the full title is called "Long-Term Impact of Hybrid Heat Pumps on Electricity Supply Security, Case Study with French Energy System." A highly relevant topic as well, as we know that electricity is now one of the key points in the energy crisis that we have in Europe. So I hand over to Dr. Wang, and then we can start now. So the floor is yours.
Thank you, Mr. Lund. So just began to share my screen. Just need to confirm. Could you see
yes,
my?
we see everything is okay.
So good afternoon, everybody. So today I'm glad to share visions, understandings on the long-term impact of hybrid heat pumps on electricity supply security, with a case study on a French energy system. So this study is co-authored by Professor Janez at Center for Applied Mathematics at ParisTech in France. And Mr. Antoine Monet, who works at GIDF at Strategy Direction. So the first context of our study is about the environmental challenge to achieve carbon neutrality in France. So after the participation to Paris Agreement, France has made a commitment to reduce its carbon emission. So the country targets to reduce about up to 40% of national carbon emission compared with 1990 level, and achieves completely carbon neutrality by 2050. So to do this, it is necessary to reduce the emission of energy usages, especially for residential sector, which is one of the major contributor to the national carbon emission. And according to the national statistics, the carbon emission of residential buildings is around 63 million tons of CO2, which represents around 25% of national level. And the very high emission of residential building sector is principally due to its fossil-based energy balance. So we see that from the pie chart that still around 30% of energy consumption is still of natural gas, and 11% of is of oil products. So to reduce residential carbon emission, we have to invest in more efficient and low carbon equipment, of course, such as solar thermal system, condensing boilers, energy retrofits, which improve the energy efficiency of buildings, and of course multiple types of heating pumps. And for the future, it is not enough for us to only consider residential sector, as the national environmental goal is over all the sectors. And in the meantime, we have to consider that we have quite limited decarbonized energy sources and maybe very limited financial capacity to invest. So we have to consider as well and rather optimized distribution of efforts among energy use sectors. So to tackle on this research question, we propose to use a bulk energy prospective model of times family. So times can achieve a technical economic optimization, and its objective function is minimizing of total discounted cost of an energy system. So our research is based on times Frank's model, which is a variant of times model applied to French energy system. So times Frank's model represents the entire energy system of France, including several sectors, such as extraction, import of primary energy resources, energy transformation, and end usages. So the model is very technology rich, and it contains over 3,000 different technologies, and it can represent in particularly in detail the final energy usage by 5 sectors, which is residential, industry, tertiary, transport, and agriculture sector. So in short, by times model, we can have economic optimized solution of energy perspective with systemic vision. So for speaking more about the model, here with a simplified description of electricity and gas system by times Frank's model. So the electricity and gas production is very detailedly represented in times. So for electricity, we have modeled around 100 types of power plants, including all existing nuclear power plants in France, different types of thermal power plants, renewable electricity production, such as wind park, solar power plants. And we model as well the dynamics of peak electricity production. Of course, the import, export of the electricity through the interconnection network with neighboring countries. For the gas production, we have independent process for biomethane production by several types of technologies. And in times frames, we can capture the some type of the dynamics of energy system by using by introducing time slice. So in the model, for 1 year, we represent 4 seasons and 3 daily levels, including daytime, night, and peak hour. So in total, we have 12 time slices. So this allows to along with the detailed representation of electricity system. This allows us to consider very specific energy supply demand situation for a certain period during the year. For example, in peak period, the electricity load for residential buildings is much higher, and the availability factor of the renewable electricity plant is lower. Here is an optimized solution proposed by Times model to achieve carbon neutrality for 2050 horizon. Here, for this result, we applied a rather strict emission constraint by supposing that there will be no further development of CCS industry. So it's a carbon capture and storage. And the figure on the left is evolution of final energy consumption for all energy sectors from now till 2050. And the right figure is details of residential energy consumption and other sectors. So we can see from the result that there will be a gradual electrification for France in the future, and the electricity consumption rise from around 380 terawatt-hour in 2020 to around 600 terawatt-hour in 2050. And apart from electricity, we see renewable energy sources such as biomass, geothermal, and biogas as well important solution for decarbonization. For residential sector, we see that the heat pumps will play a very important role in 2050, and there will be around 100 terawatt-hour of production by heat pumps. So this type of result confirms that it could be beneficial for to invest in heat pumps for residential heating. First, I would like to give a short introduction of the operation of the technology. So heat pump can extract heat from outside environments, and by a thermodynamic circle to produce heat for space heating and hot water production for houses. And in ideal conditions, the energy efficiency of heat pumps can reach to over 3 and to 4, which means that with 1 unit of electricity input, can provide 3 to 4 units of useful heat. However, the main shortage of heat pump that its energy efficiency is highly dependent on outside temperature, and under extreme conditions, the coefficient of performance will significantly reduce, as presented by the figure on the right. When the temperature is below 2 degrees, the coefficient of performance is always under 1.5. Of course, it depends on the outlet temperature of water. So in case of a massive integration of heat pumps in residential sector, the energy system can have a very high peak electricity demand. And the capacity of electricity grid might not be sufficient in this case. It could be a very risky situation for the electricity supply. And for the long term, an overinvestment in grid expansion could happen if the grid, the supply system is only designed for peak demand. And of course, we need as well consider extreme cold situation, which might worsen the supply. So under this context, we have hybrid heat pump as an alternative solution to the conventional standalone heat pump. Hybrid heat pump is composed by a smaller heat pump unit, usually 5 to 7 kilowatts in terms of electricity capacity, and condensing boiler. So compared with a standalone heat pump, a solution can switch energy input depending on, of course, energy efficiency. So usually in extreme cold situation, the hybrid heat pump will use only gas boiler. And when the outside temperature is higher, it switches to heat pump. So in this case, this type of flexibility brought by hybrid heat pump could be beneficial for energy system, as it can reduce the peak electricity power call, which is sort of guarantee of supply security. And for long term, the system does not have to invest a heavy capital in peak power plants. For this study, we try to out the long-term impact of heat pumps and hybrid heat pumps on the electricity supply system in France. More specifically, for the first step of study, we want to know the future investment choice concerning the variety of hybrid pump technology by French energy system on the carbon neutrality context, their roles in residential energy system by prospective optimization model. For this study, and for the specific research, we have developed and improved the modeling structure for heat pump strategies, heat pump technologies, by considering their different operating mode, energy efficiency over different temperature ranges, and interpretation of extreme cold climate situation for the future. For the model, we propose to present 5 types of heat pumps, including 2 levels of hybrid solutions, which is air sourced, and a type of ground source heat pump, and 2 types of classic air sourced heat pumps. So for each technology, we in the model we disaggregate it into 3 independent process instead of 1 for the past research. For example, for hybrid heat pump, the 3 processes correspond to the hybrid heat pump equipment of warm and extreme cold period. And for each period, the equipment will take different energy inputs with different efficiency. So the table on the right is a hypothesis of coefficient of performance that we have taken in the model, and we foresee a general improvement of performance from 2035 for all types of heat pumps as a result of technical progress. So next, we try to interpret an extreme cold period in the model by simplifying as a percentage of heat demand from warm, cold, and extreme cold period for all the time slices in time France. So first step, we refer on climate situation of winter between the year of 2018 and 2019. So as we can see, in France, the temperature of this winter in general remains warm, but there were several consecutive cold waves in January. And this might be quite similar to a future situation on the global warming context. And for calculating the ratio, we take statistics of efficient temperature and thermal sensibility. So for introduction, efficient temperature is related with temperature level of 2 past days, and it allows to consider the building's thermal inertia when estimating the demand profile for a household. And we define the extreme cold period is when the temperature is below 0. The cold period is the outside temperature between 0 to 3 degrees, and one as temperature above 3. So our calculation first carried on department level, and the distribution of national is then obtained by gathering the information of 95 departments of metropolitan France, except Corsica. So here I will not develop in detail the calculation method, but maybe we can see it in the paper. The calculation gives us a result as 4% of total heat demand, extreme cold demand, 90% of heat demand from cold period, and 77% of heat demand from warm period. So by interpreting this in the model, we present here our results of 2 scenarios. So one scenario with possibility to invest in hybrid heat pumps for residential buildings, and the other only possibility to use conventional heat pumps. So the figure here presents the evolution of final energy consumption for space heating for residential buildings till 2050 in France. With in both cases, a considerable part of space heat is produced by heat pumps. So on the scenario of with possibility to invest in a hybrid solution, there will be 13 terawatt-hours of electricity consumption by hybrid heat pumps, allowing for, as consequence, usage of 40 terawatt-hours of ambient heat from the atmosphere.
2 minutes. 2 minutes.
And we can see that biomass is still very important heating sources for French houses. And the thermal solution can reduce over 50% of final energy demand for space heating in both cases. So next, I would like to present you the installed capacity of space heating equipment in residential buildings. So we can see that in 2050, there will be 20 gigawatts of hybrid solution installed in residential system, which equivalent to around 2 to 3 billion of households. And so the total capacity required for space heating is around 108 gigawatts in case with a hybrid investment, so which is slightly lower than the only hybrid only heat pump case. This is because there is the gas boiler. There will be less gas boiler remaining in the housing stock. So next is a result concerning the annual fixed cost for heating equipment. So the annual fixed cost here present here includes investment cost and fixed operation and maintenance cost. So you can see that we need rather heavy investment cost due to hybrid integration in residential buildings. And from 2040, the annual fixed cost for space heating equipment is quite higher than the case without. So for the conclusion, we can see from the modeling results, the heat pump will play an important role for decarbonizing future energy mix. So under carbon neutrality context, the heat pumps can cover around 100 terawatt-hour of residential heating demand. And we have proposed methodology that enables integration of heat demand for different temperature ranges, so warm, cold, and extreme cold periods in a systemic long-term planning model. So as a result, the system chose to invest important capacity of hybrid heat pump since 2040. And in 2050, the residential buildings will install 20 gigawatts of heat pump, which is equivalent to 2 to 3 million of houses. So for the future work, we plan to include more parameters such as behavior factor, behavioral inertia of household investment, as the equipment choice is not always fully optimized among households. We can as well consider the case when the effects of thermal insulation is not as good as we expected. And finally, it's important to compare our results certainly with visions from institutional stakeholders in France. So thank you for your listening and looking forward for your questions.
So thank you very much, Dr. Wang, for your presentation and very, very detailed scenario analysis on the heat pumps. And we have time for a few questions here. Any questions from the audience? Let's check that. Now, I have a question. I mean, one question on your one of conclusions is that because of the poor COP of water air pumps, heat pumps where you use air as heat source, you need some backup. So you need the gas boiler hybrid system. Would that also not be very important in terms of the resilience and energy security? I mean, if you are 100% kind of a reliance in heating on electricity, right, like heat pumps. So if you have a let's say electric system disruption during the winter time, then you kind of lose the heat. So you need to have some kind of fuel-based backup. So would your hybrid system in a way also be as a reserve power to bridge any problems with the electric system, any disruptions that you may have? So the question is that in a way, when we think about the heat pump-based heating systems in broad way, you still need some fuel-based heating for the cold period normally, but then also for unusual situations where you don't have electricity. But you need to have heat. In a way, the fuel would be very important.
Yeah. Thank you for your vision, Dr. Lund. Yeah, that's exactly the beneficial aspect of hybrid heat pumps in case of this type of we see that supply risk, so that the electricity capacity cannot supply all the heat demand in the individual sector. So the hybrid solution, the hybrid heat pump is composed by a fuel-based boiler, which is not mandatorily use gas. We can as well use biomass or domestic fuel, something which is not dependent on the electricity system. So yeah, for sure, this and the study and the result of study shows that this solution is can provide some sort of resilience and could be beneficial for the system and could be a long-term choice under optimized economically optimized situation.
Great. So as a follow-up, if you look on normal conditions, so we have the winter. So if you look over the whole year, on the heating of the heat provided by a hybrid heat pump. So how much would come from the heat pump side, and how much would come from the gas side? So how many percent would be gas, and how many percent would be electricity?
In the current version of results, the hybrid heat pump is mainly used for the warm period, which is only operate on the heat pump, and the cold period, which use a mixed mode. But till now, we do not observe a very considerable usage of gas boiler for the current version of results. We think this is because we have applied a very strict emission constraint on the for the optimization model, because which means that the possibility to use gas is very limited at the end of horizon. But observe around 4 terawatt-hour of gas consumption by hybrid heat pumps, and it's very, I think it's very interesting point for us to explore different possibilities for, especially for the situation of input of gas for the future work.
Yes, and indeed, if we think about the slightly longer term, where we may have synthetic fuels from hydrogen beyond 2030 or like that, so that may also, in terms of emissions, give you some release and a better result. I think we are actually already ending our time. So let me thank you, Dr. Wang, once again. And as we are short of time in the conference, and we have gone through our presentations, I would then thank all the three presentators, Dr. Dell'Olio, Dr. Dolšak, and Dr. Wang for the very interesting presentations. And indeed, to our audience, I would just suggest to take a look into papers when they appear. I think the details are there, and will be interesting to look also forward to the results that you present there. So thank you once again for your presentation, and thank you for the audience also joining us today. And then I just close now this session. I wish you a very nice afternoon still. Thank you very much.
Thank you. Thank you very much, Dr. Lund. Thank you.
Bye.
Thank you.
Bye.
Okay, bye-bye.